Hi, everybody. Can you hear me all right? Excellent. I'm not used to having these bright lights on me, but my name is Leah Peterson. I'm the Adult Programs Coordinator here at the Bell Museum of Natural History, and I'm very pleased to welcome you tonight in our partnership with the Minnesota Institute for Astrophysics. This is the second lecture in an ongoing series, a hopefully ongoing series of astrophysics lectures. This one is going to be introduced by Dr. Evan Skillman in just a moment. We were talking about Zooniverse tonight. And I just wanted to say the Bell Museum has also had the privilege of working with several of the scientists and projects that are also a part of the Zooniverse complement, including the Snapshot Serengeti, which you see up here, and the Andromeda Project, and Ancient Lives, and you can check these things out by going to the Zooniverse website. But I'm going to hand this over now to the director of Minnesota Institute for Astrophysics, Dr. Evan Skillman. Thank you all for being here tonight. Dr. Skillman.
Okay, thanks, Leah. I'm really happy that all you could make it here tonight. Could I just see a show of hands? How many people were here last fall to hear Clem's talk? So we have some repeaters, okay? This is good. Good to know. Tonight's speaker is Lucy Fortson. Lucy got her PhD from the University of California, Los Angeles in physics. And from there, her first job was in Frascati, Italy, which I just discovered if you Google that, you find out that that's the wine that's characteristic of Rome. But it turns out the National Institute for Nuclear Physics in Italy is there too, so it had something to do with it. From there, she went to Chicago. Well, she was at the University of Chicago. She then started working at the Adler, and she worked there until they made her vice president of research. And so she kind of ran the place after that. It's a little bit risky to talk about Chicago right now because I know that the Wild are playing with the Blackhawks and the White Sox are coming to town to play the Twins. But as far as I'm concerned with regard to Lucy, it's Minnesota 1, Chicago nothing, because Lucy is now with us. So I'm really, really happy to have her here. And without further ado, I'll let her continue on.
Thank you very much, Evan. And indeed, Minnesota 1, Chicago nothing. Minnesota 2, actually. That's an in-joke. Okay, so those are kind of bright lights there. The better to see the cheetah with. This is a cheetah from the Snapshot Serengeti project. And if you look closely, it is actually built, every pixel in the cheetah is built of galaxies. This, incidentally, forms some of the artwork that's in the new physics and nanotechnology building. But the reason why I like it, apart from the fact that a postdoc who works with me, Kyle Willett, made it, and it's really cool, and it made it into Pan, is because, to me, it represents not only the fact that all creatures here on Earth are made of star stuff, okay, and stars are made in galaxies. Right? So all of the materials to make cheetahs and humans, et cetera, are made inside of galaxies. And so we can use that analogy here. But also, it represents the possibilities that we can do with citizen science with the Zooniverse project. And so tonight, I'm going to tell you about our adventures from galaxies and classifying galaxies all the way up to, I won't talk too much about cheetahs and classifying cheetahs, but you'll get the gist of the range of projects that we can do with the Zooniverse. And then I'm going to go beyond the Zooniverse and talk about what's next and how we at the Zooniverse are maybe getting a little too clever for ourselves and trying to use techniques that are used by Amazon and Google to recommend things. And so we're building out these kinds of functions within our machines to help make all of our volunteers happy in the work that they're doing in classifying everything. Okay, so let's get started. So this is to the Zooniverse and beyond. And I hope that I will convince you by the end how crowdsourcing science is solving big data problems in astronomy. Okay, so We all know what these are. We just saw a bunch of them. This is the interactive portion of the talk. Galaxies, okay. Awesome. Woo! Good, all right. So, how about these? Also star stuff. Condensed in a different way, right? Yeah, but they're boats. Okay. Or ships, actually, right? They actually are ships from the First World War. And it turns out that we even have a project from the Zooniverse that uses ships like these. Anybody know what these are? Wow, somebody even knew they were cancer cells. That's pretty good. Oh. How about this? Oh, not the mummy, but the stuff on the right. It's ancient writing. It's not hieroglyphs, but it's writing on papyri. Okay? And finally, hurricanes or cyclones, depending upon which hemisphere you come from. Okay, so what are all of these? Why am I showing you all of this stuff? Well, it's probably pretty obvious, but so these are all images from research projects that rely on analysis of complex images and pattern recognition capabilities that are currently beyond computer algorithms. Okay? So computers are really, really, really good at manipulating numbers. Okay? You know, they can do billions of operations a second if you want to ask them just to multiply a few numbers or divide or subtract or whatnot. Right? Computers are not very good at pattern recognition in complex images, at least not yet. Okay? Okay, we all see the tiger, hopefully. Those of us in the past who didn't see the tiger, of course, their genes are no longer with us. So we can all see the tiger. So which is better? Okay, I just gave you the answer. Computer, 5-year-old child, right? Because the 5-year-old child has that human brain that has been optimized over millions of years of evolution to be able to distinguish the tigers from the rushes, right? So that is why the human brain is such a good pattern recognition machine. So, complex images. So some of the most complex images that we deal with are galaxies. No two galaxies are the same. So they come in two basic different types. We have the beautiful grand design spirals over here on the left. They are characterized by a lot of star formation, and that is why they tend to be bluish, because as it turns out, star formation, when a galaxy has a lot of active star formation going on, it emits in the part of the electromagnetic spectrum that is in the bluish region. The other type of galaxy is called an elliptical, because it's basically a blob of stars. Okay, so it's this fancy name, elliptical, for a blob of stars. It can have, a concentration of stars in the center, or it can just be really bland and just a blob of stars. Okay, ellipticals tend to be reddish because they no longer have much star formation going on. And as the stars age in their life cycle, they tend to emit more in the red part of the electromagnetic spectrum. So the Galaxy Zoo story starts with about 100 years ago when Edwin Hubble, actually could start a little earlier than that, but let's take Edwin Hubble, who had several tens of galaxies At the time, he didn't even realize necessarily that they were outside of our own galaxy, so he thought of them as island universes, and one of his tasks was to image these so-called island universes and determine their distances. So the thing that he had to do was he had to distinguish their morphologies, okay? So he had to do pattern recognition on the different types of galaxies. So spirals, ellipticals. Edwin Hubble himself could take the tens of galaxies that he was working with and put them into a classification scheme. Because after all, another evolutionary tick that humans like to do is to classify, okay? We need to be able to distinguish, again, going back to the tiger in the bushes, right? We have to discriminate. You know, that's not a bad word in the end. It saves us from the tigers, right? So we learn to classify because we have to put things in bins in order to survive. So classification is something that's inbuilt as well. So we try to classify things, and Edwin Hubble started us on this process of classifying galaxies. So the issue becomes when we get to more than just, tens of galaxies. You can still have perhaps a graduate student when you're taking images of galaxies on photographic plates, and maybe there's tens of thousands of galaxies that need classification. You could still have a graduate student go through all of those, and that would be okay. The real issue occurs when you get to the point with the first digital sky survey, which is the Sloan Digital Sky Survey that started, basically taking data in its first guise in the 2000s and imaged 1 million galaxies. At that point, the graduate students look at you like you're crazy if you ask them to look through every single one of those images and decide whether it's a spiral or an elliptical. Okay, so that is where we are now, and that is effectively the beginning of the story of Galaxy Zoo, which we'll pick up in a second. But to presage the end of the talk and to set up why and what big data is, this monstrosity is called the Large Synoptic Survey Telescope. It is the Sloan Digital Sky Survey Telescope on steroids, okay? So this guy is going to, we hope, going to be operational in the 2020s, and it is going to increase by 4 orders of magnitude the number of galaxies that will be coming down off the sky, okay? So whatever we are doing now with the data from the Sloan Digital Sky Survey, we really have to sort out how to analyze that data if we want to get all the knowledge out of the Large Synoptic Survey Telescope that we can. So clearly, from the Sloan Digital Sky Survey days, we've had to rely on computers to be able to process that much data. Again, the graduate students are just not going to do that for us. Okay, so we have then what we call the data deluge, or big data, or there are many ways to refer to this problem. I found this image, and I think it's kind of fitting that, you have this wave of information coming out of our laptops and our other sensors. So we have, our smartphones are taking so many pictures, and those pictures are going up on, all sorts of social media places that I've never even heard of, that my son hasn't even heard of. So there's just so much information out there, and to figure out what is useful information from what is like another set of cat photos is the trick. So we are drowning in data. And data, again, coming from satellite systems, from ocean sensors, from earthquake sensors, data from everywhere. Okay, so we are in this so-called information explosion then. So the amount of information is growing, and we people at the National Science Foundation like to characterize this growth in terms of this alliteration of volume, variety, and velocity. One would hope there would be veracity in there as well. So we have, but the idea for us is this variety concept, and that is sort of the complexity of the data. And so we see that there's so much information that's coming in, and yet the ability for our computers to keep up with the analysis of that data, the growth curve is down here. So we are experiencing this horrible analysis gap. There's all of that data out there, and we frankly don't know what's in it. Okay? So this is a plug for all of you who are in any kind of science, technology, engineering, math field. Keep going. Do your best to learn data science, and you too can figure out the unknowns in that data. Okay. All right, so if computers are having problems keeping up with all that data, they might need a little bit of help. Okay, so we already know the answer to this. The best algorithm that can process complex data is the human brain. Okay, hopefully the machines haven't taken it over just yet. They're working on it. So that's fine. And as we'll hear in a minute, when I pick up the story of Galaxy Zoo, one human brain can do a lot in a very short amount of time. But what we're really after is computerizing the human brain, right? So how can we parallel process all of the information that's coming in, the complex data that's coming in? We know the human brain is really good at processing complex data. We do that by linking them all together into a crowdsourcing system. Right? So crowdsourcing isn't just used for science, it's used for many things. I taught an entire course on it last fall, so I'm certainly not going to go through all the details on crowdsourcing here. But crowdsourcing is, when applied to science, another term for it is called citizen science. So it's the ability to collect and analyze information through the efforts of the crowd. Not always in a volunteer fashion, but typically we refer to it in a volunteer fashion. Okay. So picking up the Galaxy Zoo story, the question was, we have 1 million galaxies from the Sloan Digital Sky Survey. And we have this interesting point that I made earlier, that most elliptical galaxies tend to be red, and most spiral galaxies tend to be blue. Now, to really understand galaxy evolution and why that is, you might want to ask the question, hey, are there actually any blue ellipticals, or are there any red spirals? And so up to that point, the computers that had been developed by the smart people who knew how to do, computer software, they were able to pick out the blue spirals and the red ellipticals because they used, in fact, color as a proxy. Okay, so instead of trying to design a computer algorithm that could look at the shapes of the galaxies, they just relied on the well-known fact that most spirals are blue and most ellipticals are red. And because color is effectively a number, a single number, that's an easy computer program to write. Okay, so they used as a proxy color for morphology. But as I say, what if you're a graduate student who happens to be at the University of Oxford, who happens to be interested in this question about red spirals or blue ellipticals? Then, well, you can't rely on the computer algorithms. So what do? You go out and you try to classify as many of those 1 million galaxies from the Sloan Digital Sky Survey as you can. And you get through 50,000 of them in 1 week. which is a lot to get through. So this graduate student is named Kevin Shawinski. He took out his postdoctoral supervisor at the end of that week, and I think they went to a pub on a Friday, and I think that's where most British people are on a Friday evening. And they talked about the fact that Kevin was not going to do anymore, but they still had nearly 1 million to get through. So they came up with this idea, hey, why don't we put this on the web? We can design an interface and have anybody, you don't even have to know anything about galaxy evolution. You don't even need to know what a galaxy is. You just need to be able to use that human pattern recognition capability to differentiate between spirals and ellipticals. So this is the interface that they put up. Had very simple buttons. It's elliptical, it's spiral. They had an interesting thing early on where they wanted to check to see if there was the same number of spirals rotating clockwise as counterclockwise. So if you give that a second's thought, you should imagine that there shouldn't be any difference. Okay. If somebody wants to ask me a question about that later, I'll talk to you about that, because they actually measured a slight preference in the beginning. So they launched this in 2007 in July, and this is a chart of the number of hours. So the first 2 days after launch, and this is the number of classifications per hour. So we have a Shawinski, okay? It's not bad as a graduate student, get a unit named after you. So number of classifications, right? Shawinski in a week, 50,000. They were already, all the people contributing classifications of galaxies, they had, and this is cumulative, right? So we're all the way up to 50,000 galaxies being classified before we are at 48 hours. So Kevin Shawinski can go to the pub as much as he wants while the public is helping him do his task. Okay, so what happened here? This is interesting, because I might not be standing here if somebody hadn't gone in and fixed the fact that the server, the story I hear, and I'm not sure this is really physically possible, but it melted, okay? So there were so many hits on that server at Johns Hopkins University that the claim is it melted. Some guy was willing to get up at 2 a.m. in the morning, Eastern time, and go in and swap servers, and then away we went. So it also didn't hurt that the PI of Galaxy Zoo was connected to the BBC and was able to get some good publicity for the project. And so this is CNN's most popular stories, I believe the week after launch. So we made it to number 2. Scientists seek galaxy hunt help. Right below, man flies to wedding a year early. But fortunately above, garlic may cut cow flatulence. So then, time goes on. Well, we fall below. Huge dog is reluctant media star. Okay, the mole story rose up to number 1. I'm not going to talk about my mother holding me down. That's a bit weird. So in the first 6 months, this is the total number of classifications, 40 million classifications. Okay, remember, we only had 1 million galaxies to get through. 6 months. 6 months. Kevin Shawinski and Chris Lintott, the guys who devised this, thought it was going to take 3 years. Okay? Actually, it turns out they weren't so far off. If you calculate this out, it turns out to be 3.3 continuous person years. Okay, slightly different scale than 3 years of a bit of people's time here and there. But 3.3 continuous, 24/7, 365 days a year, person years, compacted into 6 months of effort. Well done. So what does that mean? that means that each of those million galaxies got classified on average 40 times. So for the first time in galaxy morphology studies, instead of having one expert go in and say, I think that's a spiral, that's an elliptical, et cetera, and publish papers with these morphologies, and everybody would take those morphologies classified by the expert, and he was an expert, so that's the morphologies they would use for their studies. Here, we have 40 classifications. We use the wisdom of the crowds, okay, to converge on I'm making it sound simple, but there's actually a lot of science and understanding how to do the weighting of all those 40 classifications per galaxy. And you can converge on basically a probability for each galaxy. So if you think about it, if you have 40 classifications, and let's say we're thinking about spiral galaxies, 40 out of 40 classifiers saying it's a spiral, and we're thinking about spirals here, that's 100%, right? So it's 1 over here on our probability distribution here. So all of these galaxies in the blue are represented as spirals. So this would be the pure spiral sample. Here, 8 out of 10 people would have said that it was a spiral. All the way down here, 0 out of however many classifications say it's a spiral. Therefore, because it's a binary selection, all of those had better be ellipticals. Okay, so we see we have a pure elliptical sample over here. Now, of course, there's all of this stuff in the middle where 20 people said it was elliptical, 20 said it was a spiral. Okay? So at first people thought, that's really bad. Why do we have so many down in here that people just couldn't tell what they were? But in fact, if you use these and go look at them, they turn out to be interesting galaxies. Okay? You can't tell whether they're an elliptical or spiral because they may have components of each in them. Okay. So what we now have is the ability to assign a probability for the morphology of each galaxy in the Sloan Digital Sky Survey. And another point I want to make about the process of classifications is through this chart here. It's a lot of pretty colored boxes. Comes from volunteer contributions to another Zooniverse project called Old Weather. Old Weather is the project which used those ships and the logs written on those ships, the log books written on those ships, and transcribes all of the weather information. And it is used, that weather information is used to feed into climate change models. Because the only real information we have on the ocean starts in the 1970s when we have satellites and the temperature, the weather information over the oceans from the 70s. So in order to extend the lever arm back in time to get more accurate climate change models, we use the fact that World War I happened, and the British are really, really good at registering data every 4 hours to the minute, whether they're under attack or it's tea time or whatever. They are, every 4 hours, they are putting in the weather data. So we get really good, consistent weather data from all of those ships on the oceans during World War I. So we can extend the lever arm back to climate change models. So that's the idea behind the Old Weather project. What is this chart then? This chart is the volunteer contributions. So each box is one volunteer. So volunteer here, lots of volunteers down here. The size of the box is a measure of the number of transcriptions that that volunteer made. Okay, so what can we do with this information? This is a nice visualization, again, made by Kyle Willett, the postdoc who works with me on Galaxy Zoo. If you think about it, then the entire area of this graph is the total number of classifications. Now, if you cut it down the middle, right, we see on this side, half of the total number of classifications have been made by volunteers who hang out on old weather a lot. Okay? They do lots of transcriptions. Half are made by people who come and do maybe 1 or 2, or 10, or 20. But then that's enough. We never see them again. Or maybe they go off to a different project. The point being that this data is as useful to us, and in some ways more useful to us, than this data over here. In order to make sure that our classifications are meaningful, we need to have multiple independent classifiers. Because there's such a thing as expert bias. So the more you work on a project, the more expert you come in the material, this guy over here, and the more you start making assumptions. Oh, I've seen stuff like this before. I'm going to take a shortcut, and I'm going to assume blots. Okay? Novices are very careful because they don't know what they're doing. So sometimes they get very tired very quickly of not knowing what they're doing, but they've still left us 2 or 3 transcriptions, and that's very valuable for us. Okay. Okay, so I hope I've made 2 points in the case for crowdsourcing research. Right? We have the scale of the problem. We've got the Large Synoptic Survey Telescope coming up in 5 years, 40 terabytes of data a day. The Sloan Digital Sky Survey ran for roughly 10 years, and that entire database was like a terabyte. Okay? So we know that we now have the largest professional classification from the Sloan. Okay? We have a huge amount of effort done in only 6 months. And for the first time, we have measurable accuracy of the morphologies of galaxies. So if we want to apply this to any other kinds of research, we have to do a bit of homework. First, we have to figure out whether it was just the pretty pictures of galaxies. Of course, we know what the answer is. I just showed you old weather, and you know snapshot Serengeti. Okay, you know we solved these problems. The other question is, can we get the attention of the crowd? Okay. So when we think about moving beyond Galaxy Zoo to the Zooniverse, we recognize that there's a lot of infrastructure built in place already. We have, as I mentioned earlier, we have all of these instruments and simulations and sensor networks and the transcriptions from all of these projects like Old Weather. And eScience is the set of tools and technologies to support all that data federation. And eScience then is used for the analysis and data mining, et cetera, et cetera. And then eScience is also this backbone. It's the technological backbone. It's the infrastructure that allows us to do citizen science today. And so before I tell you what the answers are to the 2 questions, we're going to say a little bit about the different types of crowdsourcing. So crowdsourcing can be very passive. You are crowdsourcing if you've turned on your phone the ability for Google to measure your velocity when you're in your car speeding down the highway. Okay, so Google can monitor real-time traffic conditions from all of you who have turned that feature on your phone. So that's passive. You're not thinking about it per se, right? You've just enacted it, and that data is flowing in. the more common and, let's say, venerable, if you will, type of citizen science or crowdsourcing is data collection. This is an indigo bunting, and to study the migration pattern of indigo buntings, the Cornell Lab of Ornithology launched not just indigo buntings, but many birds, launched the eBird Citizen Science Project so that people around the United States and Mexico would cite indigo buntings and send in information on the sightings of these indigo buntings. And with all of that information, I mean, this is, thousands and thousands of people across the United States doing this. They can provide a good map, in fact, quite an excellent map, of the migration pattern of the indigo bunting. Okay, so under this heading as well, we have other types of citizen science like amateur astronomy, star counts, these kinds of things, variable star observing. But because of e-science then, e-science allows us to move into this realm of data analysis. So the idea would be then, if we can solve the human attention problem, and if we can solve the question of, okay, I can't believe I've just forgotten the first question, but never mind. So if we can solve those two questions, then we can say that Zooniverse could be exploiting this niche, so the data analysis niche. Oh, there they are. Okay, how much time and why would the crowd be interested? So we did a motivation survey asking people why they contributed to Galaxy Zoo. 20,000 people answered that survey, which is a lot of people to answer any survey, but especially in the realm of motivation for something like citizen science. What we found, to our surprise, was that the most common reason why people were motivated to work on Galaxy Zoo was they wanted to contribute to real research. Okay, so that's a pass. So it wasn't that the pictures of the galaxies were beautiful. 9% of the people said that was their primary motivation. It wasn't because their teacher was making them do it. So contribution to research, that's pretty impressive. So then the next question is, do they actually have the attention? And so we have this thing called cognitive surplus. And this is boxes that were made up by Clay Shirky. And this is representing the 200 billion hours in 2010 that adults spent watching TV. And this tiny little box down here is the 100 million hours it took to create Wikipedia. There's cognitive surplus. And of course, that's where the real cognitive surplus comes in, Okay, so we have cognitive surplus, and we have the motivation that people want to do research. So, hey, let's build an infrastructure that allows any kind of research project that wants to work on complex data. Let's build that infrastructure and give them effectively a front door so that all of the citizen scientists who are interested in contributing to research can go to one place, one portal, and they can pick and choose which projects they are interested in. Currently, we have over 1.3 million volunteers worldwide contributing to 37 projects and growing. I can't keep track of all the projects. They launch, it's like popcorn now. Ranging from astrophysics, climate science, biology, humanities, nature, physics. We have over 500 million classifications. Here's an interesting point. We have over 100 peer-reviewed publications based on that work that the volunteers have done. Okay, so that means they really are contributing to research. Funded by National Science Foundation, Google Global Impact Award, Sloan Foundation, Leverhulme Trust in the UK, and we're operated by the Citizen Science Alliance. The University of Minnesota is one of the main partner institutions of the Citizen Science Alliance. And we have recently launched an initiative here at the University of Minnesota to pull in more research from the University of Minnesota and put it on the Zooniverse. So it's not just about getting people to classify. It's supporting them in the work that they do. So every Zooniverse project has to have a discussion tool. Okay, so, and we'll see why that's important in a bit. All right? We also have to make sure that the scientists or the research team behind a given Zooniverse project are communicating with the volunteers. We have found that, much to the dismay of certain non-active science teams, that if you don't interact with the volunteers, they go away. So we have blogs, we tweet, we do all sorts of stuff to keep people interested and engaged in the project. And as I said, each project, if your science team isn't engaged, it's probably not going to be a successful project. So since 2007, when Galaxy Zoo launched, this is the number of signups. I need to get a new one. This stops in 2012. But this red curve is the cumulative signups. You can see each blue spike here is the launch of a project. So you can see that as people come on, they come on in droves, and then they lose interest and fall away, or maybe they shift to a different project. Okay? But the cumulative number of people keeps growing. And we monitor, we have, it's like, NASA mission control in the Zooniverse headquarters. There's all these displays, and people are looking at them and making sure all the projects are healthy, and, bugging the science teams when they're not doing what they need to be doing, and that sort of thing. And this is a cartoon schematic of how it works. So you have a visitor, and there's this classification interface. The classification interface then passes the clicks, the data from the classification, to none other than a classification processor, piece of software. That piece of software then pushes it to what we call a consensus engine. It's that part of the software that tells us if we've reached 100% probability on something, or close enough to 100% probability that we don't want to actually show that image anymore. That links up to the retirement system. So we don't want to keep showing images if we already know what the answer is, right? So we want to take the images out of the system. So that's the retirement system. And then, depending on how the team wants to run it, you can have a random selector of the next image that's going to be shown into the classification interface, and it starts all over again. Along the way, we realized we had sort of encoded this sort of ethics of citizen science. We would not accept any project if it was not going to lead to valuable research, or research, right? The idea would be that it would be publishable research, because we had to respect the time of the volunteers. The time of the volunteers could not be wasted. And again, that means that a machine algorithm couldn't have done the job that the humans were doing. So we must acknowledge the volunteers in publication, and as I said before, we must keep the volunteers informed of the progress. Okay. So what else can we do with the attention of the crowd? Here's another interactive portion of the talk. Expert versus non-expert classifiers. So we have the same set of galaxy images here, top row, bottom row. The blue and red dots are measurements taken on people who have eye tracking devices on them. and it registers the micro movements of your eyes as you're looking at an image on a page or on the screen. And this basically, that motion is, total several microseconds. Okay? So the red points are dwells, where there's a few, it dwells a little bit longer than the scanning motion that is represented by the blue dots. Just by looking at the complex pattern of the blue and red dots on each of these images, how many people think that the top row represents the expert classifier? Okay, does that mean by process of elimination that everybody else thinks that the bottom is expert classifier? Or how many people don't know? Yeah, it's okay not to know. All right, so what we're looking at here then is you have somebody looking around a lot on this image. Not so much down here. Here they're tracing out the spiral pattern of the arms pretty well. Very, without error or without meandering off to get further information. Okay, here it's slightly confusing because they've gone meandering off a little bit here, but that's to try to see if this is a tidal tail or a feature of a spiral galaxy. So as it turns out, the bottom is an expert classifier and the top is a non-expert classifier. And so what we find is that non-expert classifiers tend to want more context when they're making their decisions. Because they're non-expert, they want to be careful. They're not necessarily sure of exactly what they're looking at, so they look at the field as well as the object in the middle. This turns out to be a very important thing for us. So I mentioned that every Zooniverse project has a discussion forum. So the first discussion forum was put up in self-defense because when Chris Lintott and Kevin Shawinski launched Galaxy Zoo, their inboxes were flooded with, how do I do this? What is that? Hey, I made a discovery. Yeah. So after 2 weeks of this, they built a forum and basically said, talk amongst yourselves, because we got to keep the thing going here. Okay, so the discussion forum was built. And along comes this woman, Hanny Van Arkel, who was not only a global moderator, as it turns out, she was a hero member. She'd done lots of classifications. She finds this tiny little object here, and she posts it on the thread of the Weird and the Wonderful, name of a thread that the people who work in the Zooniverse, they call themselves Zooites. That was their name. They chose that for themselves. So the Zooites had made this Weird and Wonderful thread. She posted this image of something that looked like a green pea with the humorous title, Give Peas a Chance. Before we knew it, many other people were working in the peas core and were finding peas. And they were talking about mushy peas and world peas, and they were having an excellent time, okay, on their forum. No astronomer was watching. It went for 6 months, actually 4 months first, before Kevin Shawinski noticed. 4 months. 25 or so volunteers talking to each other about world peas and et cetera. But not only were they making jokes, they were studying the peas. Because almost by chance, when they launched the project, they put this number, this meaningless number. What volunteer will go up there and look at that number and go, hey, yeah, I know what to do with that number. Okay. So that number, as it turns out, if you click on it, gets you to this page. This page was made by the Sloan Digital Sky Survey as a synopsis of all the information, parameters about whatever object it is that you're looking at in the Sloan Digital Sky Survey. So here we have a green pea sitting in the middle here. That's the image. And these are people. Hanny van Arkel is an elementary school teacher in the Netherlands. We know that many of the people that were working on the peas, we had a barrister, the proper British name for some kind of lawyer. We had an accountant. We had several people who were in the realm of assistants. They had time. They were working together to figure out what these peas were. Because what they noticed is that each of these peas had this funny line here. Most galaxies don't have this. They just have a more or less smooth line going down here. This is called a spectrum. The people working on the peas project, they didn't know what a spectrum was. They just recognized that each pea had this pattern that was different from all the other galaxies. So they put that information together, and after several months, the first 4 months, Kevin Schwinski went in and answered one question and then never came back for many more months. And eventually, it got to the point where they kept emailing Chris and Kevin saying, look, we think we've made a discovery. Can you come please look? So eventually they did. And, holy cow, yes, you've made a discovery. This is a kind of galaxy we've never seen before. And so at that point, they asked a graduate student, Carrie Cardamon from Yale University, to work with the P volunteers to gather the information and write a paper about the discovery of the green peas. So I guess I'm running a little short on time here. So peas, it turns out that there were 4 green peas that happened to have been imaged by the Hubble Space Telescope. This is the resolution from the Sloan Digital Sky Survey. You really can't tell what's going on with the green peas in this image. But with the Hubble Space Telescope, you can see that, in fact, green peas may actually be a collection of blobs. It turns out green peas have a very, very high star formation rate. And, well, I don't have time to go into a lesson about green peas, but the bottom line is they're a very different kind of galaxy that may actually end up giving us some hints about how galaxy evolution occurred. They may be local versions of galaxies that started to form much early on in the history of the universe. And I'm going to skip that slide. So the first paper was published in 2009. And since then, the study of green peas has become sort of a veritable cottage industry amongst full-blown astronomers. And it's the name that has been given to these galaxies, green peas. Another, as it turns out, Hanny van Arkel was pretty good at spotting interesting things. Another interesting thing she spotted, she called voorwerp. With anybody speak Dutch? No. Okay, so voorwerp means object in Dutch. So we called it Hanny's voorwerp thingy, actually. And so this is what, I mean, of course she's going to see this and go, what? I mean, this looks really weird. All right, so what is Hanny's voorwerp? So it turns out that there is a kind of phenomenon that had been predicted to occur, but nobody had ever seen it before. The idea is that you had a jet of material emanating from this galaxy at one time in the past and illuminating some gas here. All right, so if you have some sort of merger process that pulls gas out from the original galaxy into a tidal tail, along the way igniting a quasar, and that quasar has a huge amount of radiation that's beamed towards this particular area of the tidal tail. And that radiation ionizes the gas, and then the gas glows in this particular green color that's picked up by the Sloan Digital Sky Survey. But we see Hani's Vorwerp effectively as if it's on its own because the quasar has turned off. So it had been previously thought that quasars have a life cycle, a duty cycle. They turn off, they pump a huge amount of energy down their beams, and then something causes them to quench and turn off. But nobody had ever observed anything that could provide evidence for that turnoff. So this is the first evidence that was found of a so-called turnoff point of a quasar. So that is what we think Hani's Vorwerp represents. And since then, many Vorwerpes have been, little Vorwerps, have been found by many Galaxy Zoo volunteers. And they're just kind of pretty images, so we'll go through a few of them. Very bizarre-looking objects. Unless you think that it's only Galaxy Zoo that ends up producing discoveries made by the public, I'm going to spend a few minutes describing some, actually just one discovery made with the Planet Hunters project. So the Planet Hunters project is using the Kepler mission, which itself is looking for planets around nearby stars, using the so-called transit technique. And the idea here is that you have a light curve. You're measuring one star's light over time. And the amount of light can dip for a whole host of reasons. But it can dip. Imagine if you have a planet going in front of the star. The light will diminish if that planet goes, and will pick back up again as the planet passes. So this is the transit technique for discovering planets. So you would see a wobble or a deep dip in the light curve of the star. We were really, really afraid when we launched this project because this was serving up data to the public. Okay? These weren't pretty pictures of galaxies. This was, unadulterated data. And we were sure it was going to bomb. But it turns out it's one of our most popular projects because, after all, it's a compelling project. Who wouldn't want to discover a planet? Well, maybe. Yeah, who wouldn't want to discover a planet? That's the sound of the light curve. People like to play around with this stuff. All right, so this is then a representation of the transit. And we found again, these forums, these discussion forums, are so critically important for these serendipitous discoveries because one guy, Kanjin, decides that he can use Excel to do all of the folding. He went online and learned about planet hunting and how to do the analysis, and he did it all in Excel. And he wrote it up, and he found this dip over many orbits that, the dip grows stronger as the more orbits you fold into it, and said, hey, I think I found a planet. He was right. So he published all this stuff on Talk, and the Planet Hunter scientists got really excited because in the end, it turns out that what he had discovered was a planet going around a quadruple star system, okay? A double star system. So this is an artist's impression from a moon around this planet that is orbiting around these two stars here, and the orbit is about a half a year. And the stars are roughly the same size as our sun. One's a little bit bigger, one's a little bit smaller. And the planet itself is a Neptune-like planet, about 6 times the size of the Earth. And then about 1,000 times the distance of the Earth to the sun, so 1,000 AUs, astronomical units away, is this other binary pair of stars. So this was something that had never been found before. So, yeah, we won't go through. But basically, this just shows you the orbit structure for this Planet Hunters 1 discovery. Okay, now I'm about to show you a scary picture. Okay, he left us with this amazing quote. And this quote summarizes very, very well the essence of discovery in Galaxy Zoo and the other Zooniverse projects. Because all of the known knowns are basically the primary task. We write the primary tasks to filter out the information that we know is there, classifying the galaxies, whether they're spiral or elliptical. Okay, so those are the known knowns. Then we have the known unknowns, the things that are predicted, like Hany's foreverb. So theorists had predicted that they should exist, and lo and behold, Hany found it. Then we have the totally serendipitous discoveries, the unknown unknowns. We don't even know to not know about them. That made sense. So green peas is an excellent example of this. So serendipity, then, is another critical aspect of why you want to crowdsource research. Humans not only are really good at pattern matching, but they're really good at asking that question, what's that? That's really hard to program into a computer. And if you remember from that diagram I had of the eye charts, we had the novice wandering off, looking at different areas of the image. The experts tend to stay locked into their task. So it is probable that several experts had gone over the image that contained Hany's foreverb, but it just focused on the galaxy. Or thought, I'll think about that other weird-looking thing later. Of course, we can do a lot of education work with this, but that would take an entire talk to talk about that. So the last thing I want to touch on in closing is this concept of machine learning. So this is where Zooniverse starts, I won't say, flirting with the dark side or what have you, but we do want to maximize or optimize the efficiency of the humans that are working with us on these tasks. Because after all, if you remember from the ethics, we don't want to waste anybody's time. So if you can find a machine algorithm that does the work that the humans are doing, then we take the project down because it would waste the human's time in doing it. So what we find is that what we want is we want to build a system where we have machines represented by their CPUs, and humans represented by HPUs, the human processing unit. And if you combine those two in a very smart way, very clever way, then you can optimize the whole thing so that the humans are doing what they're best at and the machines are doing what they're best at. So if you have all of this big data flowing into your system, and you've got this analysis gap you have to worry about, of course you're going to hit it with machines, but now we also know that humans should be in the loop as well. because we have all of those unusual events that the machines don't know how to deal with. But the humans do. Or at least they know to ask the question. And then the science teams can come in and help. Okay, so all that data flowing in, the machines do their best at classifying. The stuff they don't know how to classify, they push over to the citizen scientists. The citizen scientists make these new classifications and cross-checks. That creates new data sets that then allow the machines to have better algorithms. So the computer scientists can then improve the machine learning. All right, so we have this loop, and at the end of it, we have the most efficient process for gaining knowledge and closing that analysis gap. And I am just going to touch briefly on the fact that we've done this already with the Supernova Zoo project. We put ourselves out of business. We had a bunch of data taken in real time with the Palomar Transit Factory out in California. That data was piped to citizen scientists. An email blast went out saying, okay, we have data coming in from the telescopes. Please go see if you can compare a reference image to a new image. And then you subtract them, and you can see if there's a leftover bright spot there, and you've probably detected a supernova. So we had people doing this literally in real time. We had hundreds and hundreds of images coming off of the Palomar Transit Factory, and we had complaints from volunteers who said they left their office. They'd get that email, they left their office, 20 minutes later they were home, and all the classifications had been done. And that was unfair. We should have saved some for them. But the reason why we needed to do it in real time is because supernova are very short-lived. Right? And so the Palomar Transit Factory is a relatively weaker telescope, and you want to get the follow-up with perhaps some of the much bigger telescopes, which are much more expensive. So you want to know that you're giving them the best information possible. So you needed the humans to be able to filter the potential false positives out of the list that was given to the follow-up telescopes. And the humans did that very, very well. In fact, they did that so well that the Palomar Transit Factory scientists were able to use the information that the humans provided through their clicks to train their machine algorithms and improve their machine algorithms, so they no longer needed the humans. So we took the project off. And that's that story. But in my final few minutes, I want to play you a movie. And this is it'll take too long to explain exactly what these things are called. We call them Toblerone plots, but this is time along this axis here. And these are, one vertex is not supernova, and the other vertex is definitely supernova, and this vertex here is meh, not sure. So we're going to play it, and we're going to see over time the user's classification. You'll see them learn, and then you'll see something interesting happen. Okay, so, all right, so this guy's thinking it's not a supernova. So these are each different events, okay? All right, so they trained a bit here, and then they're pretty consistent with what they think is a supernova, what they think, something happened. All right, this, firstly, is an interesting point here. We are collecting all of the clicks. Of course we are, because that's the data that we use to pass off to the science teams for their analysis. But we can analyze the humans as well. All right, so at this point here, if we're getting the information that maybe that person gave their laptop to their 6-year-old daughter, maybe it would be a good idea to tell them, hey, you need to take the training or tutorial again, right? So it allows us the opportunity to intervene in the experience, in the user experience, to guide the volunteer to do things that we think the volunteer would be good at doing, they might like to do. All sorts of interesting things open up with this type of information. Of course, it could have been that he went to the pub and came back and classified. All right, so we can learn when to give which volunteer which classification task. Same thing that Amazon does when you click on something. It says, hey, your friends recommended blah, blah, blah. Same kind of idea, same kind of interventions. Well, hopefully this is for good. All right, so lots and lots of more data. So where does this leave us? So in closing, I want to try to knit all this back together again and think about where citizen science is going to be in 5 to 10 years' time. 5 years when, we hopefully have data coming in from the Large Synoptic Survey Telescope. All right? So we have, 30, 40 terabytes a night. The idea is that it's, going to repeat visit locations on the sky. I don't exactly know what the cadence is. Some people say it's once every 3 days, once every 4 days, 5 days, whatever. The bottom line is it's looking for transients. Okay, so it's looking potentially for killer asteroids or more of those supernova, right? It's effectively making a movie, not just single images. So there are going to be 10,000 of these transient events, or so-called alerts, per night, that the machines will not necessarily know what to do with. So we have to have our citizen scientists, trained up and ready to deal with that flood of data, because believe me, that analysis gap is only going to grow larger once we start getting hit with this amount of data coming in. So that relationship then between the algorithm and the eye is about to go up a notch as well. So we need an algorithm or a set of algorithms, and by algorithm I mean the combination of the human and the machine that are capable of classifying the vast majority of the data coming off the LSST, or else the taxpayers should be angry, but can make decisions about what to send for human classification. So together, the machine, part 1, and the human, part 2, can work together to pull off all the knowledge from the Large Synoptic Survey Telescope. And to be able to do that, we have to train them on this generation of data, which is one of the things we're doing here at the University of Minnesota with my colleague Claudia Scarlata and I. We're working on ways to improve the training of the machine algorithms with data from Galaxy Zoo, so that when we hit that flood of data from LSST, we have found a generic solution that can help solve the problem of that analysis gap and the flood of data coming in. And just to say that this isn't just a problem in astronomy, it's a problem across almost all of research. And the Zooniverse can apply the techniques it's learned from Galaxy Zoo and the field of astronomy to most of the other research projects that it works with. And so I'd like to end with a field of galaxies. And all of the projects have this logo feature. So if you see anything like this, you know it's a Zooniverse project. Right? It started with the Galaxy Zoo project, which incidentally is a supernova, which is also kind of weird. Anyways, so thank you very much for your attention. Good man, good man. Okay, the question was the plant. What did I have to say about galaxy spin? Okay, so if you think about it, there is no real up or down in space. So if you have a galaxy that is a disk galaxy that is rotating, if you're looking at it from above, it should rotate, let's say, in the clockwise. If you're looking at it from below, it should rotate the other way. Right? So you would think, because there shouldn't be any preferential orientation on the sky for galaxies, or should there be, then you would think that that number would come out 50-50. So it turns out that number came out to be more like 53-47, which was a little worrying. So one of the reasons why I wanted to touch on this is because it turns out there's a bias in human, there's a human bias in looking at things that are rotating. And the idea is that I think the preferential bias is to anti-clockwise, if I remember correctly. Thank you very much for that. So what we did to control for that bias is we took all of the galaxy images and flipped them, right? And that's how we found that it actually wasn't something cosmological. It was just in the machine, the human machine. So, yeah. Yeah. Yeah, so gamification is something that when we have our collaboration meetings, we sit and we think. We've tried gamification. So the old weather project, you can be a captain if you finish a logbook, okay? But we did a study, and we found that that turned a lot of people off. It was too competitive. So the people who would come on, in fact, Galaxies Zoo launched with a leaderboard. And we found it was turning people away. Because in certain types of citizen science, you're after as many of these independent classifiers as possible. You don't want to turn anybody away, right? So you don't want to necessarily have the guys or gals that are sitting there, getting really, really, really good because they want to be the best. Okay. So for the longest time, we've decided no gamification. But we are beginning to explore ways in which we can gamify without it being as blatant as a competition. So yes, we know, and we work with social scientists at a variety of institutions that are helping us try to understand the motivation and how to, how to manipulate people, basically.
So how did Penny become a Galaxy Zoo hero?
Yeah, because she had a lot of time on her hands, and she just loved it, and she started. Yes, so very good point. Okay, so that was at the beginning when we did have these leaderboards. Right. So, but another interesting point about this is that you want both. You don't just want to throw away all the people who are doing really good work, because they typically are the ones that monitor and moderate the forums. They have the experience to do so, and you want them in there moderating the forums. Okay, so not only was she a hero member, but she was also a moderator because of her experience. So there's a very open question as to, again, it's manipulating humans, right? And manipulating their motivations and trying to figure out what job is best for each person who comes onto the system. Yeah. The fact that a person stays on for what becomes an expert, so to speak, by doing many, many classifications, could that not introduce bias? Okay. So the nice thing, though, is that you've got 40 other people to control for that. Typically, this depends on the project, but typically you would take away the first few clicks that a person does. And do you remember from Andromeda what happened there? No, okay, yeah. So it depends on the project, and if the project is something like a transcription project where, let's just say the consensus process is different depending on the project. And that question is driven by the consensus development. That's a really good question. So the question is, he noticed that I had the citizen science project called Foldit listed. And Foldit is not a Zooniverse project. Although, interestingly, the guy who started Foldit and I went to high school together. So the idea behind Foldit is they're looking for ways in which proteins fold, and they're trying to find the minimum energy state for proteins when they are folding up together. And this is something that it's very difficult for machines to do, but it turns out that humans, again, are really, really good at finding this minimum. It turns out it's a game for humans, okay? Now, the reason why that's really interesting, it ties back to the game question. Foldit is exactly the kind of citizen science project you want to turn into a game. Foldit, you're not looking for multiple independent classifiers. Foldit, you're looking for the best guy, okay? So you're looking for the person who for whatever reason, intuitively knows how to fold proteins. So that's where you want a leaderboard, and you want round robins, and you want any competitive process to get the best people up at the top. So we've learned that from Foldit, and that's one of the reasons why we think about gamifying what we do. No, and you've hit on exactly okay, let me repeat the question. So the basic question was, are we going to end up losing the serendipitous aspect of all of these projects if we automate the whole process? If what we're doing is developing the procedures to train the machines better such that it becomes completely automated, then where's the human in the whole story? So when you have so much data coming in, like with the LSST, there's always going to be stuff that the machines can't classify, or at least we believe that is the case. So the humans are always going to be working on the edge. So they're always going to be, effectively riding the big data wave and picking off the stuff that doesn't get classified by the machines, continuously improving the machines, and maybe a couple of us were talking a bit earlier. Maybe one day the machines will do it all, and who knows what our role will be in the world at that point.